All right, we'll go ahead and get started. We're right at 10 o'clock. Thank you everybody for joining us for this Saturday morning speaker series. We are kicking off the first speaker today with Andreas Schmittner on climate change, hoax or apocalypse. And we will be hosting a speaker every Saturday at 10 a.m. through March, excluding holidays. We currently have our schedule up through December. So you can check out more information on that at capeperpetualcollaborative.org and click on the events tab. Next week, we are hosting the presentation, A New Kid on the Dune, the unlikely hybridization between two non-native beachgrass species in the Pacific Northwest. And before I turn it over to Andreas, I want to quickly highlight the Cape Perpetual Collaborative and the organization coordinating this series. And their vision is to foster a conservation and collaboration within local communities. And they have three guiding principles: community engagement, leveraging resources, and engaging in partnerships. And we have a variety of partners from state, federal agencies, as well as some local nonprofits and the Coos Lower Umpqua Siuslaw tribe. The focus of the collaborative is around the Cape Perpetual Marine Reserve, which is the largest of 5 marine reserves in Oregon. The Marine Reserve is 14 square miles, and with the marine protected areas to the north and south, its protected waters span from Yachats to Florence. And one fun fact for today about the Marine Reserve is that Cape Perpetual Marine Reserve and marine protected areas host some of the most biologically diverse rocky intertidal area in the entire Pacific Northwest. And the collaborative organizes a variety of community science projects, as you can see here. Some of them are seasonal and some of them are year-round. And we also are hosting a Young Scientist webinar series the second Tuesday of the month, October through April at 5:30 p.m. And we are in the throes of preparing for our Land Sea Symposium on November 19th in just a few weeks. And so again, you can find out all the events and the webinars that we're hosting at capeperpetualcollaborative.org and click on the events tab, and you can go through the calendar there. Please feel free to connect with us on our Facebook page, Cape Perpetual Marine Reserve, and we are also just recently launched our YouTube channel, the Cape Perpetual Collaborative. We will be hosting replays of our webinars on our YouTube channel, so feel free to check that out once you, if you want to go over there and watch some replays of our past webinars. In a little bit, you'll see on your screen, you can post questions to chat or to the Q&A. So feel free, if you've got questions, to post them there, and Andreas may take some throughout his presentation, and then we can cover any that we didn't get to at the end of the presentation. And with that, I'm going to go ahead and introduce Andreas. He's a climate scientist and professor at Oregon State University. And as a professor in the College of Earth, Ocean, and Atmospheric Sciences, Schmittner teaches coursework in climate change to students from a variety of disciplines. He recently published an open source textbook called Introduction to Climate Science in an effort to make the content free to students and widely available to members of the public. He continues to analyze the ocean circulation and global climate, considering a variety of factors from heat transfer to biogeochemical processes to greenhouse gas emissions. Schmittner also maintains an active public voice in his efforts to educate the general public in climate change. With that, welcome, Andreas. I'm going to let you share your screen now. Oh, Andreas, you are on mute.
I see. Okay, can you hear me now? Hello?
Yes, we can hear you now.
Okay, sorry. Well, good morning, everybody, and thank you for tuning in to a presentation on climate change during these tumultuous times when people have other thoughts and other things on the top of their mind. But at least it looks like we've gotten a little bit of uncertainty, so the decision seems to be made regarding the presidency. But yeah, now, and so with all that and the coronavirus, people, I guess, weren't that, it was not on the top of their minds, the issue of climate change for some time now. But it's not going away, so it's still an issue. And yeah, Tara already gave a little bit of a background, and I just want to tell you here why I'm doing this, and also maybe a little bit more background about myself. If you hear an accent, I'm originally from Germany, and I've did my PhD in Switzerland, and have been in Corvallis at CEOs and OSU for since 2005. I'm a physicist by training, and have been working on this issue for more than 20 years now. And I'm interested in kind of conveying the science aspect to the public, because if you just follow the news and the internet, there's really so much misinformation out there, and really these diverging ideas and opinions, where one side, or some people think that we're the catastrophe or an apocalypse is near or almost inevitable, whereas you hear other people saying it's a hoax, it's not even happening, or as our current president did some time ago, he said it will change back, so suggesting essentially that it's not a human caused issue. So I would like to tell you about the science, what we know, what we're really certain about, and what we do not know, where there's uncertainties. So science is never really fully settled, so we're still trying to understand many things, but for some things we're really, really sure, and I'm going to tell you about those as well. Let's see if I can forward here. But I want to have as much feedback and back and forth as possible. So feel free during the talk to type your questions in the chat window. And we will also have some time at the end for Q&A. So please let me know what you want to know. So what are your questions about climate change? Okay, so I thought, we may start with a little poll. So maybe we can, Tara, could you activate the poll now? Let's see if this works. So here are, I'm just interested in your thoughts about current climate change. What do you think? So here we have the hoax is the first option. So that means it's not happening. Then number 2 is happening, but it's due to natural factors mainly. Number 3, it's happening, but mainly human caused. And then there's the other questions are about, whether or not it's a good or bad thing. So number 4 is a good thing, and number 5, it's bad but manageable. Number 6, major impending catastrophic effects with possible end of human civilization. So that would be the apocalyptic option. Or, I don't know if you don't know. And you have multiple answers. So you can, for example, check it's happening due to natural factors, but then also it's a good thing or it's a bad thing. So because those are not mutually exclusive. And one more thing I want to say, and feel free to start filling in the poll. These first 3 questions, that is something that science can tell us about, or these answers. So science can tell us about if it's happening and if it's due to natural or human factors. But what science does not tell us is if it's a good or a bad thing. And that, because that requires value judgments. But nevertheless, science can inform those value judgments because science can tell us about the impacts of climate change. So what are the consequences? So it can help this decision, but ultimately, if the good or bad decision, that is a value judgment, so that requires ethical considerations, and therefore it is outside of really the science. Okay, so let's see. It doesn't seem like. Okay, I can't vote. I'll just click it away. So hopefully you've all been able to fill in. Tara, I don't know, do we want to look at the results now or later? Can you see?
Yeah, I can go ahead and do it now. Let me click end poll and I will share results. Can you all see that?
Yes.
Okay, there we go.
Okay, so so most of you think that it's happening and the human cost. Nobody thinks it's a hoax. And then the opinions about good or bad. So nobody thinks it's a good thing, but some think it's bad but manageable, and others think it, maybe catastrophic. Okay, great, thank you. Now, what do scientists think? And there, of course, we need to have a very specific question. And here the question is if it is human caused or not. And here the scientific community has a really clear thinking, and essentially all of climate scientists do know that the current global warming that we're seeing over the last 50 to 100 years or so is human caused. And I've just selected here three statements from major scientific organizations. The first one is from the National Academy of Sciences. The second one is from the American Geophysical Union, and the third one from the American Meteorological Society. And all of these three statements essentially say the same thing, which is that humans are the main cause of the current global warming. It's mainly due to greenhouse gases that we've been emitting into the atmosphere for, since the industrial revolution. So really, there have been also studies kind of trying to quantify the consensus amongst the climate science community. And, there's somewhere around 97%. So almost all climate scientists who really work in the field do they're convinced by the evidence that the climate change is human caused. And I'm going to show you some of the evidence that has convinced the scientific community that this is the case. But the public has quite different thoughts about this topic. So if you ask kind of the same question, here is global warming caused by human activities, you get only about half of the population that thinks that is the case, as indicated here in these orange, yellowish colors. Whereas, many people think it's mainly caused by natural changes. And, that discrepancy between the scientific community and the public is mainly what's driving kind of my personal outreach activities. So that motivates what's motivating me to, get the message out, to better communicate, hopefully, to the public, the scientific findings. And there's a lot of misinformation out there that contributes to this confusion in the public. But there's also a lot of good information out there, and the trustworthy information, some of which, I just wanted to give you some resources here. And Tara has already mentioned the textbook that I wrote recently. The link is here in the upper left. And you can also Google, I think if you would Google climate science texts, Oregon State or something like that, you would be able to find it. And then there's various scientific reports from that typically involve the whole or a large part of the climate science community, such as the IPCC report on the upper right here. That's the Intergovernmental Panel on Climate Change. That is an international body that is from the UN. So scientists from all countries participate in that. And here's an example of one of the latest reports. This one is an ocean and the cryosphere. So that's the ice sheets and ice in a changing climate. And so those reports are really typically very dense and thick. So, you know, thousands of pages and hard for the public really to read and understand. But they also publish what they call summary for policymakers, which are a little bit more digestible. So if you're really into it and want to look at those documents, look for those summary for policymakers and have a look at the at those statements in there, because they reflect what the majority, the consensus of the scientific community. So that is really what scientists think. And then on a national level, if you're interested in more local issues, you can also look here at the National Climate Assessment on the bottom, which is also regularly published and available. So there are regional parts. If you're, for example, interested in the Pacific Northwest, there's a chapter on that or a sub-chapter that you can explore and try to find out what is going on here. Okay, let's move on to the data then. So here is kind of the basic temperature record over the last 100 plus years. So you can see it's starting on the left here in the year 1880, and then it goes to the present year 2020 here on the right. And what is shown in the vertical axis is the temperature anomalies. So it's a difference with respect to some base period, which in this case is 1910 to 2000. At the around 1900 or so, the temperatures were lower than the base period, and then now they have been rising since then. And now they're about, we're about something like a degree or so warmer than we were 50 years ago, and more than a degree warmer than we were 100 years ago or so. So, and that is degrees Celsius here on the left, the scale, on the right scale, you can see the Fahrenheit. So in terms of Fahrenheit, we have increased temperatures on the global average temperatures by about 2 degrees Fahrenheit or so. And you can also find always the link to the information here down there if you're interested. You can go there yourself. So what does that mean? So this means that the temperature measurements with thermometers that we have for the last 100 years, they document a clear warming trend. So there's no doubt about it. And you know, if you look at this curve, you see one year is a little bit warmer or colder than the next year. So there's this fluctuations from year to year. But overall, there's a strong warming trend, and particularly over the last 50, 60 years or so. And you know, each decade essentially is warmer than the decade before. Even though, you know, from year to year, you can see small fluctuations. For example, 2019 has not been the warmest year on record, but that has been a few years before. But it has been the second warmest year on record. So warm records are much more common now than cold records, and that is also consistent with the global warming climate. Now, this is the global average, but of course we all live in certain regions. So let's look at a map here of how that is regionally different. So this map shows the surface temperature change from the 1950s to today, or 2019, where we have good data. And as you can see in these yellow and orange colors, it's warming everywhere around the globe. There's only this small region near Antarctica where there's cooling. And in the North Atlantic, there is also a region, this white region here, where it's not warming, and in the North Pacific. But overall, almost everywhere it is warming. And you also can see that the warming is not uniform. So it's not warming the same everywhere, but rather some regions are warming more, like for example, over land, it's warming more than over the ocean. And in particular, the Arctic shows the largest warming. So there we have seen these red colors here indicate more than 2 degrees, between 2 and 4 degrees Celsius warming over that 70-year time period. And over land, it has been warming typically between 1 and 2 degrees Celsius, whereas over the ocean, it has been warming less than that, only between 0.5 and 1 degree or so. And we do understand those mechanisms that cause that larger warming over land versus the ocean, and larger warming over the Arctic pretty well. And I can, if you're somebody's interested, I can talk about that, why that is the case. So there's multiple different data sets. So the data that I've just shown you is only surface air temperature measurements, but there's also measurements of temperature in the ocean. And you can convert that to heat content simply by multiplying by a constant heat capacity factor. And then you get the curve like this for the upper 2,000 meters for the last 80 years or so. So you see the heat content of the ocean has been steadily increasing, and the blue curve shows the measurements from ships. So when people, oceanographers, go out and they take measurements, they lower an instrument into the deeper waters and pull it back out, and that's the way we used to get subsurface ocean, deep ocean measurements. But since about 2005 or so, we have this red line here, which are cargo floats. So those are autonomous, essentially robots that float in the ocean, and they can dive to different depths and stay there for a while. And once in a while they pop up and they measure during their ascent to the surface, they measure the temperature. And then when they're at the surface, they send the signal back to the satellite and to the labs where we can record them. And you can see that both the blue and the red lines, they show the same warming trend. So it's really clear that the upper ocean has been warming over the last 80 years or so. So not only the air temperatures are warming, but also the ocean temperatures are warming, not only at the surface, but also below the surface. And there's many, many more data and measurements that support that global warming. And some of the visually, most perhaps for non-scientists impressive pictures are of glaciers. And here, this one is showing an example from Alaska, Glacier Bay. The Muir Glacier, there's a picture from 1941 in the top left, and then one from 1950 in the bottom left, and then one more recent from 2004 on the bottom right, where you can see how that glacier has retreated and shrunk over that time period. And now, there's this large lake in front of the glacier, and you also can see, more vegetation growth there where where there was no vegetation before. So really large changes in some regions, particularly covered by glaciers. And I should say those, this is a typical for glaciers worldwide. Glaciers everywhere in the world are shrinking. There's only a few glaciers that are not shrinking or advancing, but the vast majority is shrinking. So that is consistent with the warming climate. And then there are the big ice sheets as well. So here on top of Greenland, on the right, there is a map that shows where the melting is happening in red. So it's happening around the margins. And here, the time series on the left starts, I think, in year 2002 and goes to 2017 or so. And you can see, you know, a decrease, and that is the mass, the Greenland mass changes are recorded there. These are from satellite measurements from the GRACE instrument that measures gravity and can detect mass changes from gravity measurements. And you can see this decreasing trend indicating shrinking of the Greenland ice sheet of around, you know, something like 4,000 gigatons, so billion tons of mass have been lost from Greenland over that time period. And you can convert that into sea level rise, which amounts to something like 0.75 millimeters per year. So that water that is flowing into the ocean contributes to sea level rise of about 3/4 of a millimeter per year. And then in the bottom, there's Antarctica, the same thing. So we see a decreasing mass of the Antarctic ice. And the map on the right shows where that is happening. It's mainly happening on the West Antarctic Peninsula, or the West Antarctic ice sheet. These red colors there. And the sea level contribution is smaller than for the Greenland ice sheet, but, you know, overall, the Antarctic ice sheet is also melting and contributing to sea level rise. And so together, the Greenland and the Antarctic ice sheet contribute about 1 millimeters per year to sea level rise. Of course, that meltwater flowing into the ocean from these big ice sheets and from the glaciers, the mountain glaciers, they contribute to sea level rise. And then another factor is the thermal expansion of seawater. Just by warming, it's expanding and therefore also expanding its volume, and therefore contributing to sea level rise. And then there is a smaller contribution from groundwater pumping, as you can see here in this pie chart. These are the contributions from between 2005 and 2015. And the time series of tide gauge measurements and satellite altimetry measurements in red from 1880 to the present are shown in this line here that indicate also an increasing sea level. And so if you look at the numbers, so these are millimeters, so the sea levels have increased by 250 millimeters over that time period. That corresponds to about 10 inches or so. So, you know, that may not sound much, but no, it is increasing and it is also accelerating. So if you look at the trend here in the earlier part, the trend was about 1 millimeter per year. In the middle, it was 1.4, and here now currently it is rising at a rate of about 3 millimeters per year. So sea level rise has definitely accelerated. So I guess, you know, we can come back to our question here, is it hoax or apocalypse? So what we can already exclude is this one here, right? So it's definitely not a hoax, right? So it is happening. There's multiple evidence from the air temperature measurements that show warming, the surface and subsurface ocean temperatures that show warming, ice sheets and mountain glaciers melting, and, you know, many other measurements that I have not even shown you that are also consistent with that global warming effect. So clearly we can exclude that it is a hoax, and I'm glad that nobody of you thought that it would be in the poll. So, but how about, is it, how bad is it? Is it a apocalyptic or not? So let's move on. Maybe, I don't know if we will be able to answer that, but we can try. So, okay, oops, how can I, oh, sorry, I want to remove this drawing here. Okay. And are there any questions so far?
We have one question. It is about people talk about planting trees to mitigate climate change. And they wonder about Forest Service management. Should we maintain forests better so burning will be less extreme?
Yes, that goes towards solutions, and I was going to talk about solutions at the end, but it's also okay. We can do it now. Yes, so I agree that planting trees is a good idea. It removes carbon. It's a natural way how to remove carbon from the atmosphere, right? When a tree grows, it takes CO2 up from the air, and it sequesters it in the wood. That and also in the soil. So that is a way to remove carbon from the atmosphere. But planting trees alone is not enough to stabilize, to compensate for our emissions from fossil fuel burning. We'll get to the fossil fuel burning later on in the talk, but it is not enough. It is a good idea. It can contribute, and is something I think we should do. But it is, and with that also, forest management is definitely useful for that. And it can also be useful for mitigating forest fires, which I will also talk about. Those are also partly, at least, made worse by climate change. But I'll talk about that later. But so far, what what I've shown you is just data about what is happening. So warming and melting of ice and sea level rise. But we haven't talked about the cause. And so, well, we scientists, we do know the main cause of that global warming, which is the increase in atmospheric CO2 concentrations. And the basic data set is shown here. This is from measurements, air measurements of atmospheric CO2 at the Mauna Loa Observatory in Hawaii, which were started in the 1950s. By Charles Keeling, and you can see, that's the red line are the monthly data. So there's this up and down, this wiggly line, which is due to the biosphere in the northern hemisphere growing and shrinking during seasons. But overall, there's this large increasing trend, and currently we are over 410 ppm, and compared with the end of the 1950s, where we had about 320 or so. And we can even go further back in time with ice core measurements. My colleague Ed Brook, for example, at OSU is doing those. And from those, we know that in the pre-industrial, we had concentrations about 280 ppm. So we've increased from 280 to now to about 420. So, more than 1/3, we have increased the concentration of atmospheric CO2. And because CO2 is a greenhouse gas, it traps heat. It reduces the cooling from radiating energy from the Earth's surface to space. It's essentially acting like a blanket. So if you put a blanket on, it reduces the heat loss from our body to the environment. And similarly, CO2 reduces the heat loss from the surface of the Earth to space, and therefore increasing CO2 leads to global warming. And that is pretty well established fact. So there's no doubt about this. Now, since CO2 is the main problem, and of course there are other factors that influence climate, and I could talk about them. So if there's interest, please write it in the chat. I can't do that. Scientists have looked at those, for example, solar variations or volcanoes or natural ocean circulation changes. They all contribute somehow to climate variability, but this large increasing trend, the global warming that we're currently seeing, is not caused by those factors. It is caused by the rising CO2 concentrations in the atmosphere. And so if we then focus on these rising CO2 concentrations, where do those come from? We also know very well that those are from human carbon emissions. And that is shown in this graph here that shows the emissions in gigatons of CO2 per year from 1850 to the current, or 2018. And the gray area is the amount of CO2 emissions from burning of fossil fuels. So that is the main factor that caused that increase of atmospheric CO2 concentrations. There's a smaller effect of land use change. So that's this yellowish area. And then below the zero line here in the blue, that is shown what happens with the CO2 that we release into the air. Some of it is taken up by the ocean, that's the blue area. Some of it goes back into the land, it stimulates plant growth, that's the green. But a large part, about half of it, or more than half of it, about 2/3 or so of it, stays in the atmosphere, that is the light blue. And that is what we saw before in the CO2 data that causes this increase in atmospheric CO2 and hence warming. So we know that these carbon emissions here from fossil fuel burning, the gray line, they are from humans, and there's multiple evidence for that. So first of all, for example, we can count the amount of fossil fuels that is traded internationally, and that way account for how much fossil fuel is burned and used. And then there's also chemical methods, for example, carbon isotopes and oxygen measurements can also, they clearly show, they prove that humans are causing this CO2 increase. So, you know, there's no doubt in the scientific community, therefore, that humans are the main cause of the current global warming and climate change. And so, you know, this is obviously in contrast to statements from our current president, recent statements that, you know, where he said, for example, that scientists don't know what is causing it and that it could go back to you know, where it was before. That is not the case. And that is not the case also because CO2 stays in the atmosphere for a long time. So CO2 stays in the atmosphere for about for hundreds to thousands of years. And that means that you know, it accumulates there. You know, when we continue to emit carbon, it just adds to the problem. It makes CO2 concentrations go higher and therefore temperatures warmer. So it's a cumulative problem. And I thought maybe some people might be interested in the COVID effects on the carbon emissions that's shown here in this red. So the black line is the emissions from 2000 to 2020 or 2019. And then you can see this little dip here, which is expanded on the right due to COVID, you know, restricted emission, or, you know, reduced emissions due to less driving and such. As you can see, it went back a little bit, but not much. So we went down from 100, this is million tons or megatons CO2 per day to about 80 something. So, you know, in terms of history, we went back maybe 10 or 15 years to where the emissions, to global emissions, how they were then. But as we expected to come back to almost the emissions we had before. So COVID is not really doing anything major in terms of emission reductions. Yeah, so okay, so here's another graph that I wanted to show you, and because I think it's important to, it is a nice illustration and an important relationship that shows us the carbon emissions, how they are related to global average temperature. And these are essentially from data and models. And on the horizontal axis here, we have the cumulative carbon emissions. On the bottom, it's in gigatons carbon, and on the top, the numbers are a little bit different. It's in gigatons CO2. Gigatons CO2 is just 3.7 times the amount of carbon because you add the weight of the oxygen, the 2 oxygen atoms there. But the amount of carbon we put into the atmosphere cumulatively, from the start of the Industrial Revolution to today, or to whatever date in the future, that the number determines then the global warming we are getting, which is on the vertical axis here. So if we're looking at the historical data, the black line here, for example, we have put about 500 gigatons carbon into the atmosphere, or something like 2,000 gigatons CO2. And that has led to about a 1 degree Celsius warming. So if we put another 500 gigatons into the atmosphere, we would get something like a 2 degree warming, right? And then another 500 would give us 3 degree. So it's proportional, right? So how much carbon we put in there is proportional directly to the amount of warming we're getting. And so the more carbon we put in the air, the more it will warm. And we could go to something like 5 degrees before pre-industrial. There's certainly enough carbon available to do that if we wanted it. But now when many people try to stop warming, or think it is important to stop warming more than 2 degrees or 1.5 degrees, and that will be kind of already quite challenging, because we are already at 1 degree. So if we would want to stop at 1.5 degrees, for example, we would essentially, we have almost no carbon left that we are allowed to accumulate. So we should almost immediately need to reduce carbon emissions almost to 0. But even if we would want to limit warming to 2 degrees, we have only about 500 gigatons or so left that we can emit. So if we set ourselves, if we would as a humanity set ourselves a target for how much we want to limit the temperature increase, that would also give us then a target for how much carbon we are able to emit into the atmosphere. So that's the significance of this figure here. And just to kind of illustrate the amount of carbon that we are emitting, so each American emits about 4.5 tons of carbon per year into the atmosphere. And you can convert that to pounds per day. So that's about 27 pounds per day, or 100 pounds of CO2 per day, or about 10 feet, a cube of 10 feet size. And I've just calculated it yesterday. Somebody on Twitter asked me to convert it into cups. So that would be 2 pints per second. So we emit 2 pints of CO2 per second into the air, every American. Okay, and that of course then accumulates. So I think, but now the time is moving on. So I just want to say what I showed you so far is essentially things that we are very, very sure of. So we know that the warming has been caused by CO2 emissions, and we know it's causing sea level rise and melting of ice sheets and so on. So for continued carbon emissions, if we continue to emit carbon in the atmosphere and CO2 continues to rise, we can expect, we're almost sure, that this will continue to go on. So we will have more warming, we will have more melting of snow and ice, we will have more sea level rise, and many of the other aspects or impacts that I haven't talked about, like shifts in vegetation and ecosystems. So those are really very, very certain aspects. What we do not know exactly is how much warming it will be, how fast sea level will rise, and how and the vegetation and ecosystem shifts are also less certain. So how exactly they will play out in different regions. So that is something that we still need to work on much more. And talking about vegetation shifts, here's just an example. The high latitudes where we currently have tundra, for example, here with this ecosystem that consists essentially of shrubs and grasses, where currently these musk oxen live. And that will be gradually replaced by forest, by boreal forest. So those shifts are already going on and have been observed, and they will continue to happen as the climate warms. There's a lot of other impacts and concerns. One is irreversibility. As I mentioned before already, CO2 essentially stays in the ocean atmosphere system for a very, very long time, hundreds and thousands of years. So essentially, on those timescales, the warming is irreversible. And then there are effects on extreme events that are probably the most concerning in terms of impacts on people. And I'm happy to talk about those if there's interest. I have a few slides prepared. There's also positive feedbacks like permafrost melting, for example, that releases methane and other carbon from the soil and increases the CO2 concentration in the atmosphere, and therefore makes the problem worse. And I can talk about those as well. Then many people are concerned about tipping points, ice sheet melt, and possible ice sheet collapse and ocean circulation slowdown or collapse. And I have slides. If you're interested, we can talk about those. Ocean acidification is another concern that is associated with the uptake of CO2 by the ocean from the atmosphere. That produces carbonic acid in water, just like in your soda, and that acidification of the ocean has implications for animals and certain organisms in the ocean that rely on calcium carbonate shells. And I can talk about that. And then the ecosystem vegetation and growing season effects that we can also talk about. So, if you want to know more about those, please let me know in the chat whatever you want to talk about, and I'm happy to do that. And I'm just going to browse through here the ice and ice sheet ones. We can come back to that if there is interest. The sea level rise projected for the future, the ocean circulation, permafrost. Something I wanted to quickly go over is extreme events, because I think most people, that will be the most direct effects for many, many people in the near future. So what we do know is that some extreme events will become more common. For example, heat waves. Other extreme events will become less common, like, for example, cold spells. But then there is there's the effect on storms. For example, tropical cyclones, hurricanes, and typhoons will not increase in total number. So that's what we currently think. And I should say those effects are currently not very well known. So the uncertainties here, the scientific uncertainties, are much larger than for the things that I was talking about earlier. So in the total number of hurricanes will presumably, that's our current understanding, will presumably not increase, but we will get more strong hurricanes. So category 4 and 5 will increase. And because warmer air can hold more water vapor, the existing hurricanes will lead to more precipitation. They will, they will soak up more water from the ocean, and they will lead to more precipitation. And as in the case of Hurricane Harvey, that was over Houston, that caused a lot of flooding, and so that is will get worse as the air warms and the ocean warms. We get stronger hurricanes, and they also will lead to more downpours, to more flooding. The droughts will also increase because of the water cycle, the effects of temperature on the water cycle. So the air can hold more water vapor. That leads also to more soil evaporation, and therefore will intensify droughts. So we will get more droughts and more floods in certain regions. I should say though that holds for certain regions. So it's not globally a global effect. So droughts, for example, are thought to be more intensified in regions that are already dry, whereas regions that are already wet will get wetter. So those are regionally specific. And then also regionally specific are the effects on wildfires. And I have a slide, if there's interest, I can talk about effects on wildfires. But maybe I should pause here and see if there's something in the chat. Are people specifically interested in certain topics?
Yeah, Andreas, it looks like
Mhm.
there is someone that's interested in learning more about the acidification of oceans.
Okay, yeah, I'd be happy to do that. So let me just scroll to the slide here. Okay, so here on this slide shows observations from near Hawaii from 1958 to 2012. And the red line is the same as we saw before, that's atmospheric CO2. And here's the scale. And the green and the blue line, those are measurements in the ocean. And the green is CO2 ocean measurements. So the PCO2 of the ocean water, the partial pressure of CO2 in the ocean water. As you can see, the trend line here is exactly the same as in the atmosphere. So it follows essentially what is going in the atmosphere. That is because the CO2 goes from the atmosphere into the ocean and leads to an increase in CO2 in the seawater. Now, because of the carbonate chemistry in the ocean, that leads to a decrease in the pH. Remember, CO2 and water makes carbonic acid, so that reduces the pH. That is the green line here, and that has been observed to be going on, so we know it's very certain. So the ocean is, because of that uptake of CO2, is becoming more acidic. And the effect this has is on calcifying organisms is thought to be a concern. So calcifying organisms, there are many organisms in the ocean that build body parts out of calcium carbonate. Calcium carbonate, CaCO3, is, for example, these little shells of these coccolithophores, those are microscopic organisms, phytoplankton. Foraminifera are also microscopic organisms, zooplankton. And then there are pteropods here on the lower right, and of course corals on the lower left. And they all build body parts out of calcium carbonate. And because of that reduction in pH, the carbonate ion concentration of the water becomes lower. And that decreases the amount of material they have to build their calcium carbonate shells. And it also makes the water more corrosive, so it tries to dissolve those shells. And so those animals and those organisms that currently that build calcium carbonate shells, they will have a harder time in an ocean that is more acidic. But that is also a relatively new scientific topic, so we do not know a lot about the consequences of this. Which brings me to corals, which is also an impact that is of concern, because corals are affected not only by ocean acidification, but also by bleaching. So just by the temperatures. As the ocean temperatures warm, the corals that are typically healthy, like on this figure on the left here, that have these colorful zooxanthellae, which are some symbionts, phytoplankton symbionts, they are expelled when the water gets hot or warm enough, and then they look like this on the right, this picture on the right, and they are bleached, what they call bleached, so they're white, and they've lost their symbionts, and that is not healthy for the corals. So maybe one bleaching event they can survive, but multiple bleaching events, at some point they will die. And the Great Barrier Reef, the biggest kind of coral assemblage on the planet, has lost about half of the corals due to bleaching already. So corals are really very sensitive to these ocean temperatures, and they're impacted by temperatures and also by ocean acidification. And so they are already strongly negatively impacted by current global warming. Does that answer the question?
I believe so.
Are there other questions?
There are a couple other questions not related to ocean acidification, but would you like me to start going through them?
Sure.
Okay, so we have one. Does the increase of atmospheric CO2 also affect the dissolved CO2 in the ocean?
Mm-hmm. Yes, it does. That was essentially what I just showed you before here in this figure. Oops, sorry. Gonna go back. So the dissolved CO2 in the ocean is the blue curve here. Yes, and so it essentially follows the atmosphere. You know, when the atmosphere CO2 increases, that increases the partial pressure in the atmosphere, and that pushes the CO2, if you will, into the ocean. And therefore, in the CO2 in the ocean, the dissolved CO2 in the ocean also increases, right? Yeah, good question.
And then another question, we had a cyclone off the coast of Manzanita, Oregon a couple of years ago. Are we likely to see more of these?
That is something I do not know. Yeah, I don't think I can say anything meaningful regarding this. In general, I think what we can say is that storms will lead to more precipitation just because of the higher water vapor in the air. So, you know, we can make general statements like that, but not, I don't think we can make a statement that storms will get more frequent here in the Pacific Northwest.
All right. And then another one, I'm interested in predicted vegetation changes, CO2 rise effects on wildfire. Thanks.
Mm-hmm. Okay, yeah, wildfire is of course on many people's minds these days, as we had this horrendous wildfire season this summer. And it is also a relatively complicated topic that needs some nuanced discussion. And that's why I tried to put here in this graph. And the background picture, by the way, is from the Beachy Creek fire that we had this summer. So first of all, kind of some background. Wildfires are influenced by various factors, and which include fire suppression. So they're not only influenced by climate, but also by other human activities like fire suppression, which we have practiced for the last 100 years or so, which has suppressed smaller fires, and many people think it has led to the fires that are burning to become bigger. So that is one factor, but climate is definitely a factor in wildfires as well, because, well, how do wildfires work? Well, what you need for a wildfire is you need dry fuel, right? So dry vegetation and wood. And then if you have ignition to start it, then you get a fire. So the ignition, of course, is another issue that, you know, people can contribute to. So, you know, regardless of climate change. But of course, there's also natural ignition from thunderstorms, from lightning, which is as far as I understand, those big fires in Oregon, like the Beachy Creek, they were ignited by thunderstorms. But the dry fuel is, of course, influenced by climate. So as I mentioned before, droughts, you know, will get more because of global warming. The air can suck more, you know, moisture out of the vegetation, out of the fuel, out of the soil. So that leads to, and also the summers get longer. So both of those effects lead to what has been called the fire weather, essentially becoming more prone to wildfires. So longer growing season, longer fire season, and drier fuel, drier summers, they affect wildfires. And therefore, global warming, because it makes summers hotter and drier in our region, it leads to more and larger fires. So I think this is uncontroversial. Yes, so continued global warming in the future will presumably lead to more and larger fires in our region as well. Maybe one point also that goes back to the previous question that was asked in terms of forest management. I think that forest management can do things to mitigate these effects, and that, if we prescribe, for example, small fires to reduce the fuel load, that can definitely mitigate the situation, and so presumably help in adapting to these increasing fires in the future. But nevertheless, I think global warming is a factor, and therefore it would be good to reduce it to not increase that wildfire risk further into the future.
And then there was just one more question. If tree planting is good, why not argue that changing tundra to the forest is better?
Yes, as I said, you can arguing what is better and good or bad is requires value judgments. So that is not really a scientific question, but talking as a person rather than a scientist, if we have a conversion of one ecosystem with another, of course, that ecosystem, the tundra ecosystem, gets lost or gets smaller. So those animals and that live there, like these musk oxen here, or the Arctic fox, or the geese there in the background, they will have a harder time. So I'm not saying it is good or bad, but it is a change. And yeah, so I guess you could argue well, perhaps that leads to carbon sequestration because you replace tundra by forest. On the other hand, there's the thawing of the permafrost releases carbon. So that is opposing this effect. And so permafrost has methane stored, which is also a greenhouse gas, and carbon that goes to CO2. So both of those are greenhouse gases, and the thawing of the permafrost releases that, and that contributes to make the problem worse. So it's not that simple that just replacing a tundra by boreal forest makes this situation better. And here is a figure in terms of permafrost. So let's see. So there's I've made a note here, there's an additional carbon input into the atmosphere, but there's no runaway effect. So it's essentially what people think currently is that it's making the CO2, the problem about 10% worse. So it's not a huge factor, but it is contributing to the problem.
And then one question did roll in. Will melting of the glaciers in Greenland cause the most catastrophic event in the US and worldwide?
I'm not sure I understand that question. Will melting of Greenland cause the most catastrophic effects? Well, let me talk a little bit about melting of Greenland, and maybe that clears things up. So as we've seen, Greenland is already melting, and there's some feedbacks going on, and in our science language, we call this ice sheet elevation mass balance feedback. But it's essentially when you get warmer temperatures and melting of the ice, that lowers the elevation of the surface, and that because at lower elevation, atmospheric temperatures are warmer, that then leads to even warmer temperatures, so it leads to more melting. And so this is this positive feedback, or what maybe some people call a vicious cycle, that then reinforces that. And because of this feedback, ice sheets can irreversibly disappear, and that is indicated here in this kind of schematic diagram of ice volume on the vertical axis, and horizontally you can think of as warming. So the warmer you make it, at some point the ice sheet will drop down here and completely disappear. And then if you make it colder again, you have to go past that threshold to make it much colder until the ice sheet grows back. and that is because of this feedback. But the Greenland ice sheet is currently very close to this threshold, and we think that about another half degree or so, so a global warming from pre-industrial of about 1.5 degree would be enough to go to this irreversible melting of Greenland. Whereas Antarctica, which is much further south, much further poleward, I should say, and also higher up in the atmosphere, so it's less vulnerable. But nevertheless, in principle, ice sheets can irreversibly disappear, and Greenland is close to this threshold. So currently we think that a global mean warming of 1.5 degrees is where that threshold is approximately. Of course, we don't know it exactly, but in that ballpark. So what does that mean if we cross that threshold, this 1.5 degrees? And maybe that 1.5 degree is also why people say we should stay below 1.5 degree. That would be one reason to avoid the irreversible melting of Greenland. So here is kind of a model simulation of how that may look like. Well, you can see the Greenland ice sheet on the left, like in its current extent. And then, as it melts in a model that is run with 4 times CO2 concentrations, you can see how that ice shrinks. But also notice that the time scales here, this is 300 years, 700,000, 2,000 years. So it takes a long time for the entire ice sheet to melt. What that means is that it would not melt instantaneously, over years or decades, but it would take hundreds or maybe even a few thousand years to melt. In terms of, sometimes we talk about ice sheet collapse, we should remember that that collapse would happen over a relatively long time scale. But nevertheless, the Greenland ice sheet has so much ice stored that if it would melt completely, you would get a 7 meters sea level rise. So that is a lot. And a West Antarctic ice sheet, which is also vulnerable to warming, could give you another 5 meters of sea level rise. So the West Antarctic ice sheet has kind of a similar threshold region like Greenland, so that with a relatively modest warming, you could get both of those ice sheets to irreversibly go away, and therefore you could get something like more than 10 meters of sea level rise. So that is definitely a concern. I have here something on the West Antarctic ice sheet and come back if people are interested in it, but essentially what that means is that even a relatively optimistic carbon emission scenario, here this is from a paper my colleague Peter Clark has published a few years ago, that shows that even for a relatively optimistic carbon emission scenario, large regions of low-lying current countries, like here Bangladesh, for example, but also parts of the US, East Coast, here Florida, for example, New York and Louisiana, are vulnerable in terms of sea level rise of that magnitude. So that is definitely a concern. Something we are currently do not know very well is the rate of change. So how fast will that sea level rise occur? And that is something that climate scientists are actively working on and trying to better understand. Okay, are there other questions?
That looks like it answers all of them that have come in.
All right. So, well, if there are no other questions, I think we've covered most of the things that I wanted to talk about, and I would just leave perhaps with the idea that we are causing this problem because we are putting we're burning fossil fuel and putting carbon in the atmosphere. So we can also solve it, right? So it's not something that is out of our control. So the good news is that we can resolve it, but it will be challenging because currently our whole economy essentially works as it takes as energy source fossil fuels, or most of it. So kind of converting from fossil fuel use to energy use that does not pollute, that does not emit, without fossil fuel burning, like renewable, for example, or nuclear energy also work. That will kind of take a major effort. And so, but nevertheless, it is doable. And I personally think it is not that difficult. If we would just set our minds to it, if we just wanted to do it, I think it's not that expensive, and it is not that hard once we kind of make up our mind. So I'm kind of cautiously optimistic, especially since the results today that we have an administration now that is more that takes that problem more seriously. So that makes me a little bit more optimistic now. And with that, let me just thank you everybody for tuning in. And feel free, if you have some more questions, I'd be happy to answer them if you put them in the chat. And if not, then have a nice rest of your weekend, and thank you again.
Thank you so much, Andreas, and thank you everybody for attending. Like I mentioned, we did record this, and so we will be posting it to our YouTube channel by probably Monday or Tuesday. So you can look for it there and share it. And Andreas, I really appreciate you taking the time on this Saturday morning to share your knowledge with everybody. It's a very important topic, can be very complex. So learning all the little bits is very inspiring to see that scientists are working on this. We appreciate it.
Thanks for having me.
Yes, you're welcome. Thank you, and have a great weekend, everybody.
Thank you. Bye.
Bye.